Welcome to Engineering 311. This is Mechanics of Deformable Bodies. I'm Dr. Mike Augsburger, and I'll be with you the whole the whole class. Our first lecture is going to be our sort of beginning of our link between statics and deformable bodies, and it's called internal resultant forces. So let's just dig in. So in statics, we're normally concerned with interactions between bodies, right? Between potatoes, because physicists and engineers, we love our potatoes because they're nice and general and delicious. And so we're normally concerned with interactions between objects. In deformable bodies, we want to understand the forces and the stresses inside the body. So not between one body and another, but rather what's going on inside a particular member. What are the forces and stresses acting on the material itself? And so that's why sometimes this course is called Mechanics of Materials, because we're interested in the interactions within a material rather than in between different objects. And so we'll start off with an analysis of this potato here. And this little guy is going to help us all term long with irrelevant comments about the lecture, just to provide some distraction. To do this, to look at what's going on inside this material, we're going to use the method of sections. And you used a method of sections in statics, and this is pretty similar to that, although we're going to be more interested in what's going on, like I said, internally rather than within a structure at large. Speaking of sections. So we take our potato, and this potato here, you can see has four forces acting on it, F1 through 4. And we want to know what's going on at the marked section. So we're going to divide our potato, we're going to cut it like a scalloped potato, right at that section plane. And what we'd find is what you see at this bottom image, which is it's a really complex set of forces, right? They're going to be, that material is going to be interacting across that plane in all sorts of different ways, depending on what part of that section we're talking about. So we're going to try and simplify this, right? We know that the sum of these complex forces, all of those arrows at the top of our section, going down and up and across and so forth, we know those have to sum with F1 and 2 to be equal to 0. This is simply statics, right? If we divide our part like this, all of those forces have to equal to 0 because we know it's not accelerating linearly. We also know it's not accelerating rotationally, and so we can take a set of moments and know those have to sum to 0, right? So again, one of our core statics equations. The problem is we've got a ton of unknown forces here, right? So we don't have any way, we don't have enough equations here to solve for all those unknown forces. So what do we do with that? Well, we're going to find, we're going to sum all of those and call it a resultant force and a resultant moment. So these are what are called our internal resultant loadings. And you can see the image on the bottom right here. We've reduced all of those various individual forces to a moment, MR, and to a force, FR. And we've placed those forces are acting at the centroid of our section. So that's the geometrical center of our section here. And we'll talk more about centroids later. You probably did some of those in statics. And they come into play fairly frequently in deformable bodies. But the important point here is that we took a bunch of really complicated forces and we summed them all together into our internal resultant loadings as one moment and one force acting at our centroid. And so all of those statics equations in our sectioned part are now reduced to these two equations, right? That the sum of our forces is equal to 0 and the sum of our moments is equal to 0, right? So each F1 and F2 are going to create a moment around the centroid. We need to make sure that our moment at the centroid balances those applied moments. Now we know these are actually solvable, okay? Because if we know F1 and F2, we can figure out what our resultant force and our resultant moment is. Now, to actually solve this problem, we need to find the vector components of those resultant force and moments. And each of those components has a name and has a particular physical meaning too. So we can look at our normal force here. And that's going to be our force that's perpendicular to the face. That's this guy right here. We can look at our shear force. That is going to be our force that is parallel to the face. We can look at our torsional moment. This is the moment that is twisting our potato around its central axis, right? So we can think of this as a twisting moment. And then we have a bending moment, which is perpendicular to our sectioned face. And that bending moment is tending to bend that potato, right? So if the torsional moment wants to twist it, the bending moment wants to bend it. Safe enough. And so you can see here that there are actually, if we divide these into components, our bending moment, for instance, is going to have two components if we put this in a Cartesian system. So we're going to have two bending moments, potentially two shear forces, right? Again, if we have a Cartesian coordinate system here, and then one torsional moment and one normal force. So those are 6 components of our resultant loadings that we can name here at any given section. Now, that's pretty complicated, right? So we've got, if we think of those 6 resultant loadings, we can simplify that if we have what's called a set of plane forces, right? Or if the forces are coplanar. And that means that essentially we can pick one dimension in which no forces are acting, right? So that's fairly common in statics, and it's fairly common in deformable bodies as well. And in that case, we can reduce the number of loadings significantly, right? So we'll only have one component of shear force, we'll have one component of a bending moment, and then we'll have a normal force. There will be no torsional moment, right? Because we can't deal with a torsional moment in a plane. And so we've reduced that from 6 components to 3. And so that makes our little guy happy. It makes us happy.